We present exploiting and refining depth distributions with triangulation light curtains. We look at the problem of estimating depth outdoors. This is currently done with active sensors such as LiDARs, which can be highly accurate but have sparse depth data and are expensive, or with passive sensors such as monocular or RGB cameras. These are low cost with high resolution, but have unreliable depth or struggle in bright sunlight or low light situations. So let's look at this modality first. How do we deal with unreliable depth estimates? We can formulate it as a probabilistic depth regression problem. The following papers demonstrate the prediction of depth distributions as opposed to directly regressing on depth values or inverse depth. This means that we can use the uncertainty information to discard those unusable pixels. These methods, however, do not actively or adaptively exploit these depth uncertainties to reduce them, instead choosing to ignore the unreliable depths or just feed them back into the network for further refinement. We wanted to ask, can we physically correct for this uncertainty? If we look at this pixel and we grab the depth distribution, could we sense specific depths in the scene and reduce those uncertainties? It turns out that we can, with a type of adaptive sensor introduced in 2019 called Triangulation light curtains. This sensor lets us sample specific depths across a scene at high speed and resolution with a low cost via placement of a 3D ruled surface. So let's see how this sensor works. The light curtain consists of a 90-degree rotated rolling shutter near-infrared or NIR camera, a line laser module combined with a controllable galvo mirror, and these produce a laser plane and an imaging plane to form a line. Any object that is within this line shows up on the NIR camera image. And if a high intensity shows up, we know that there is an object there. We control the camera and the galvo mirror such that we can image or generate a 3D ruled surface on an object up to 20 meters away. Any object that intersects this surface shows up with some intensity. Prior work noted that instead of a line, there is actually a thickness to this curtain, where any object within this volume actually shows up on the NIR image. But this work did not exploit this thickness. Here we show a planar curtain being swept across the scene as it intersects with an object 7 meters away. Notice how the intensity rises and falls off in a Gaussian-like curve due to the thickness. We can model this using an exponential fall-off model. And when applying Bayes' rule over it, we can actually convert this into a depth distribution. Notice how regions with no uncertainty generate an inverted Gaussian-like distribution, and as the intensity increases, it slowly flips into a rising peak with a Gaussian-like distribution. Our goal here is to adaptively discover depth. We want to start off with a prior. That can come from a light curtain sensor or from any other modality such as an RGB camera or any preferred prior distribution of your choice, such as a uniform or Gaussian distribution. We then place additional curtains at the desired regions that maximize the information gained. Then we fuse these estimates to get a more refined measurement, which gets better over time. So let's look at the overview of our method. Here we will show how we use RGB cameras and a light curtain sensor and correct for depth estimates. So given an RGB input, such as this monocular RGB image, we can see that the depth is pretty noisy and also shows scalar ambiguity. We can see a similar representation in this top-down uncertainty field view. Now, we place curtains over regions that are uncertain using our light curtain sensor. The light curtain measurement is then passed back into our network and we get a much more refined depth estimate. So let's look at how all of this works. We start off with our state space. Given an RGB image, each pixel can correspond to containing a depth distribution with some quantization. We call this a depth probability volume. We then take a slice that corresponds to a plane just above the road. we can then collapse this into a single plane, which we call the uncertainty field. Note that the region in green is our current state, and the region in red is the ground truth from a LiDAR. Our DPV state space can be initialized from any modality, including RGB cameras via neural net, a light curtain, or from some prior of choice such as a Gaussian distribution. Here we see on the left a Gaussian distribution slowly converging on the ground truth depth with light curtain placements. And on the right, we see the same thing but starting from a prior distribution from an RGB camera. Note the improved speed of convergence and better depth quality when using a prior from the RGB camera. Before we get into the details, what does this look like in our actual experiments and our actual sensor setup? Here's a quick teaser. Notice how we discover the depth of a large object about 10 meters away, starting from our monocular prior. Observe how the distribution splits into two modalities and slowly converges in the actual object. Here's one more example. So how does this all work? We generate a prior distribution from an RGB camera via monocular inputs over time, or stereo pairs, left and right, and extract features using a shared encoder. We then warp these features into a common cost volume using differentiable homography, and we regress on that to generate a low-resolution depth probability volume. We then upsample this DPV into a higher one using a decoder and the features from the encoder. We then use this as a prior to adaptively place light curtains and refine them over time. We then feed this light curtain measurement back and repeat this process. Let's look at some examples in the Kitty dataset with our light curtain simulator first. Here we start with a prior from monocular RGB, place light curtains, correct it, and feed it back into our network. Observe how the uncertainty gets corrected and how the predicted depth distribution converges on the ground truth in the uncertainty field. Let's see that again. And now let's look at a full moving scene without light curtain feedback and with light curtain feedback. Observe the uncertainty in this object notated in yellow. We can see how the edges are pretty uncertain, and with the light current feedback we're able to refine this. And here is an example of a more cluttered scene. We start off with an extremely hazy and uncertain distribution and converge in the object within 3 frames. And here it is with the moving scene. We trained it on the Kitty dataset, and when testing with the light curtain, we enabled light curtain feedback at around epoch 16, and we immediately noted improvement in the depth over time, over epochs. Now let's look at some real-world experiments. Here, we are attempting to discover the depth of a vehicle about 15 meters away. When using monocular-only RGB inputs, we notice a pretty incorrect depth distribution. We also visualize the light curtain placement but without feeding it back. When we input the light curtain measurements, we immediately see that it converges in the object correctly. Here we show that depth distribution from light curtain only placement also does converge on an object, but it takes significantly longer and the accuracy is not as good as combining both the monocular and light curtain measurements. Let's see that again. We can plot the convergence in this graph. The blue curve shows just using the light curtain to discover depth, starting from a Gaussian distribution, and the orange curve shows starting from a monocular RGB prime. Notice that it converges significantly faster with lesser update iterations. Here's depth discovery of a large object about 10 meters away. In this scene here, we demonstrate how we trained our light curtain feedback on Kitty and then applied that same network in a real-life scenario. Our network was able to learn to incorporate the measurements from the light curtain and feed it back into our network to get a more refined depth estimate. Here is another example. Within about 3 iterations, we're able to converge on the object and discover its depth. We also tested this in driving scenarios outside. Our method has potential to generalize to fast-moving scenes if we can model the scene flow and surface properties. Notice how we're keeping track of the object by placing curtains on the objects in the scene that are moving.